All right, let's talk about object detection. For years, teaching a computer to spot things in a picture was, well, it was a real headache. A super complex, multi-step process, basically full of guesswork. But what if a model could just look at a picture and, bam, spit out a clean, final list of every single object, all at once? That's the game-changing idea behind DETR, which stands for Detection Transformer.
So, here's the plan. We'll start by looking at the hurdles of the old way. Then we'll dive into DETR's much simpler direct approach. We'll break down how it actually works, get into its really clever matching trick, and then wrap up with the results and what this all means for the future of AI.
Okay, so before we can really appreciate just how big a deal DETR is, we got to take a step back and look at the old way of doing things. You'll see pretty quickly why it was so complicated.
So take a look at this. For you and me, it's obvious, right? Two birds. Easy. But for a computer, this is a surprisingly tough problem. The real challenge wasn't just finding a bird. It was knowing there are exactly two of them and not accidentally flagging the same bird 10 different times. And this really shows you the night and day difference. The old way, on the left, was so messy. It would generate literally thousands of guesses. They're called anchors or proposals. And you'd end up with a huge pile of overlapping boxes for the same object. Then you needed this whole extra step called non-maximum suppression to clean up the mess, which is basically a fancy way of saying it picks the best box and just throws away all the duplicates. But the new idea with DTR, forget all that. It's a single, elegant system that predicts everything at once. One shot, no cleanup needed. It's just done. All right, so how on earth did they build this simpler, more direct system? Well, the genius here was that they didn't just tweak the old methods, they completely reframed the problem. They started treating object detection like a translation problem.
And that brings us to the absolute core concept here: direct set prediction. See, instead of making the model jump through all these hoops, proposing regions, refining boxes, DETR just says, no, let's treat this as one single task. The job is simple. You get an image, and you directly output the final, unique set of objects. That's it.
And the beauty of this approach is everything you get to throw out. All those clunky, hand-designed parts that engineers used to have to tweak for hours, they're just gone. No more anchor generation, no more non-maximum suppression. The whole pipeline becomes incredibly simple and clean. Okay, so the philosophy is elegant, for sure, but how does it actually work? Let's pop the hood and take a look at the architecture that makes all this direct prediction stuff possible.
So at a high level, the pipeline is actually pretty logical. Step 1, you've got your backbone. This is just a standard CNN, a convolutional neural network. Think of it like the system's eyes. It just looks at the image and extracts the basic features. Then, step 2, those features get fed into a transformer encoder. This part is amazing at understanding the global context of the whole image, how everything relates. Step 3 is the decoder. This is where it gets really clever. It takes a small, fixed number of object queries. You can almost think of them as empty slots or questions like, is there an object here? And it uses the context from the encoder to find the objects and fill those slots. And finally, step 4, you have the prediction heads. These are simple little networks that just look at each filled slot and spit out the final answer. This is a cat, and here's its bounding.
So looking at this diagram, you can really trace the data's journey. The image goes in on the left, the CNN does its thing, and then the transformer encoder and decoder reason about the entire scene. And here's the really crucial part. This all happens in parallel. Remember those object queries we talked about? Let's say there are 100 of them. They all get processed at the exact same time. The model learns to assign one query to one object. And for any leftover queries, it just learns to label them as no object. Simple as that.
Okay, but wait a second. This all sounds great, but how does the system actually learn to make one and only one prediction for each object? How does it avoid making duplicates without that cleanup step? Well, this is where the real magic trick comes in.
The secret sauce is something called a bipartite matching loss. Now that sounds complicated, but the idea is actually super intuitive. During training, it acts like an automated matchmaking service. Imagine you have the real objects, the ground truth, on one side of a room. On the other side, you have all of the model's predictions. This loss function finds the absolute best, most perfect one-to-one pairing between them. Each real object gets matched with exactly one prediction. Any prediction that doesn't get a match, it's considered wrong, period.
And what this does is incredible. It forces the model to learn how to avoid duplicates. Why? Because if it makes 3 predictions for the same bird, only one of them can be the official match. The other 2 are penalized.
So over thousands and thousands of training examples, the model learns to be efficient. It learns to use one of its object queries for one object. And that's it. It completely solves the duplicate problem right at the source.
Okay, the theory is really elegant, right? But the big question is always, does it actually work? How does it stack up against the competition in the real world, and what does this all mean for what's next in AI?
Well, the results were pretty darn impressive. Take a look at this table. The key metric here is AP, or average percentage. Higher is better. You can see that the standard DETR scores a 42.0, which is exactly the same as a highly tuned faster RCNN model. And when you give DETR a more powerful backbone, it actually pulls ahead, 44.9 to 44.0. This was huge. It proved this wasn't just some neat theoretical idea. It was a real contender right out of the box. But here's where it gets really interesting. This chart shows a fascinating trade-off. On the left, for small objects, you can see DTR actually does a little bit worse. It kind of struggles with the tiny stuff. But then, look at the right. For large objects, DTR blows the competition away. It's way better. So what's going on here? The answer, it turns out, is all about the transformer. That self-attention mechanism lets it see the entire image at once. It understands the global context, how everything fits together. This ability to see the whole picture makes it absolutely fantastic at reasoning about large objects, because it's not just looking at the object itself, but also everything around it. And it doesn't stop with just drawing boxes. This architecture is unbelievably flexible. The researchers showed that with just a few tweaks, the same core DETR model can tackle something way harder called panoptic segmentation. That's where you're not just finding the zebras, you're classifying every single pixel in the scene, the cow, the grass, the sky, the whole shebang. And you know, the authors were really upfront about the fact that this was a brand new direction. This quote from the paper sums it up perfectly. They say, look, this new design for detectors is a big step, but it's not perfect. It comes with new challenges, especially when it comes to training and its performance on those small objects. But they were optimistic that future research would solve these problems. So ultimately, what DETR showed the world is that sometimes the best solution to a messy, complicated problem isn't to add more steps, it's to take a step back and reframe it as one single end-to-end task. And that really leaves us with a fascinating question to think about. What other complex fields in AI are just waiting for someone to come along with a similarly simple, elegant rethink?